Really? I'd like to see that.
That's a good show.
Yeah.
I'll bet Snoop.
Oh, God.
Is that tonight?
And Warren G.
All right. Well, just a second ago, we were talking about biological remedies for carbon dioxide sequestration, sort of putting it back into the biosphere. This, let me show you one more thing to kind of think about. And let's see how to do this here. So I guess thinking in terms of Venn diagrams, you can sort of think of this whole circle here as nature. Some of it's alive, some of it's not, right? And Gaia hypothesis aside, and so I guess we could just sort of slice this thing and say, well, here's sort of the living, the biosphere. And again, it's not just a sphere, because even in this room, you consider each one of us is part of the biosphere, but just be honest, well, is there life in the air? Is there life back in that cabinet? So it's not like it's just a blob somewhere. It's just what fraction of nature is alive. Because I'm going to argue that, like, down here, maybe not, or like right here, who knows? Maybe there's something crawling around there, but I'm just going to call, this rock dead, not alive, not metabolizing anything, so inert, there we go. So inert. And then, with the dawn of technology, we sort of have this thing called the technosphere, which sort of bridges these two things. So technosphere. And, and we're to the point now where, these two things are very much intertwined. Just look at somebody who's like on dialysis or has, a cochlear implant, or even, I've got a couple screws in my knee from, from surgery, pacemakers, exactly. So the biosphere and the technosphere have sort of merged in a lot of ways. And so this little bridge is just a fascinating one for me to consider, because you look at this like, can't we, keep this CO2 somehow, in the biosphere, and rather than pumping it off to some weird dead zone? Because if that bubble pops or comes to the surface, there's a cool, let me show you this one reason why you might lake in Africa. Just came across this, Lake Nyos, there it is. And yeah, I don't know if you heard of this story or not, but high on the flank volcano. So obviously there are gases stored under a lot of volcanoes, and a lot of CO2 just sort of naturally sequestered under the lake. And this is 1986, as a landslide. Like 2,000 people just died as this CO2 bubble, because CO2 is heavier than air. It just sort of crept down the mountain and suffocated.
All the people sleeping, right?
Yeah.
Was it? Yeah.
And 3,500
people
cattle.
laying like up on the second bunks and stuff.
Yeah.
Okay, except for the people on the main.
Yeah, a little weird
Yeah.
to wake up dead. Yeah.
There's worse ways to die.
Well, yeah, but so you see this is a naturally occurring CO2 bubble, or burp, if you will, and like, ooh, aren't we isn't that a little bit of a time bomb? Because it's under pressure. It's under pressure the same way that the deep water, that when that thing popped, it's because you've got this fluid under all of, this rock and water, and it's like, it's just like a
Heat
big
and
pimple
everything else, yeah.
popping, right? So That's,
some concern in Canada about that.
yeah, yeah.
Is this some of the CO2 sequestration you were talking about, or the prior ones? Is this something people are already doing?
Well, yeah, and I actually, gosh, I'm blanking on the guy's name, but I'll show you another active project right here in Montana. It's the Kevin Dome.
Many houses in there.
Yeah, that'd be good to know for the future, because all these industrial companies right now know what they're doing, but then once they all go,
Yeah.
then the public is gonna have no idea, and what if
Right.
we're digging somewhere.
Yeah.
You're
Well,
just like,
Yeah, it's the same thing with, reading that summary for with, public involvement and oversight, and at least some insight into the future of the nuclear industry. But this guy's going on right now, and it's kind of fizzled. I've played golf with the PI on this. I don't know if his name is on here or not. Site characterization, modeling activities, site operations, project, permitting efforts, monitoring efforts. It's a pretty big deal. It's Lee Spangler. I think that's his name. He's a professor at MSU. And so it was a pretty big deal. Montana State Energy Research Institute. They do some algae over there as well. We took a little.
This is that pumping carbon into the ground?
Yeah, and it's up. Let's see if we can do Kevin Dome project. And for now, it's just they're basically seeing, will this thing hold CO2 underground or not? And so they've kind of been injecting it and then sucking it back out. Let's just go here and see if we can do it on the maps. It's Kevin Dome, not Kevin.
I figured after the second time you said.
Yeah. We cannot find. It is in Area 52. That might be.
There's maps all over the right.
Oh, there we go. Thanks. This is the only one I knew about.
Those are all carbon sequestration projects?
It looks like it. So,
Okay, all the codes, I'm just like, really?
let me.
We've got ethanol plant, you can,
Yellowstone
you got a lot of
is,
stuff selected.
Yeah, tell me. Oh, okay. Yeah,
You can
thanks.
deflate
What am I?
stuff.
Yeah. Electricity. What should I be clicking here?
I would unclick all the,
yeah, oh, yeah, they're all different.
Yeah,
Okay,
yeah. Thanks. I just came into this
Oh,
guy.
it's just- Oh, the CO2
Where's the-
emissions.
Where's the
See it.
Storage potential, there's,
what's coast lazy? BSCSP project?
Let's not do that. Let's do that. This might be it. Petroleum natural gas processing. Let's unclick that.
refineries and stuff.
Unclassified CO2.
This is secret, you can't know about it.
Unclassified, that means it's not.
Oh, unclassified, I thought it was classified.
It means that they can't classify it into a group.
Industrial facility, chemical.
I didn't know that
Huh.
I question everything.
I think that's it. No, Plum Creek, point source,
Oh, so this is actually CO2
Northern
emissions.
Border Pipeline. Yeah. Anyway, I thought we were gonna find it on the map there, but anyway, I think the point is they're tracking where the CO2 emissions are, and if like, hey, let's stick it underground somewhere, then it's like, okay, here, let's build the CO2 pipeline. In my opinion, I can kind of see that working. I would love to see my own, like get rid of my natural gas line to the house, just do something with solar thermal heating, but then send CO2 back through that pipeline, and then it just sort of pops up in somebody else's greenhouse around town. So I could see sort of, controlling CO2 in that fashion or manner. That's kind of my little dream or vision of integration. Okay. Technosphere, Biosphere. This is a little shot of what's going on with the flow of, well, really water.
Water and wind.
Well, it's mainly water, and I don't know if you guys have seen this much. If you're taking
That's
climate
the-
change,
That's the,
thermohaline.
Yep.
Yeah, you've probably seen this. So.
that's what keeps Britain warm.
Yeah, so what's, basically what we're seeing here, the red lines are flows that are happening at the ocean's surface, and the blue lines are flows that are happening below the ocean surface, down to the bottom.
Ocean current, there's a current at the bottom of the ocean.
Yeah, exactly. So you've got currents on the top, currents on the bottom. You can kind of think of it as the ocean jet stream, if you will. So here we are, along the equator. The sun is just, cooking this water. It's got to go somewhere. It's getting hot and it's expanding. So where's it going to go? So some of it heads this direction, some of it heads to the west. It combines with this other warm water sort of welling up. Well, again, got to go somewhere. Can't mess around with this landmass. So around the tip of Africa it goes, comes up through the Atlantic in general, and it's still got some momentum. Gets even warmer, and here's your hurricane zone. And as it's warm, the water itself is leaving, and the salts stay behind. And now it's become more dense. It cools and dives back under. But there's sort of enough, mechanical momentum and thermal momentum to keep England unseasonably warm, warmer than it otherwise would be. And so, and I'm not going to pretend to understand all the mechanics, but if for whatever reason, let's just say this says, hey, no thanks, I'm just going to sort of swirl around here and not bother heading north, then you run into large climate issues with that portion of the planet not being as warm as it would be. There's also, I don't know if you've talked much about geoengineering in other courses, but solar radiation management is mentioned right here on page 586. So so as explained in box, the Earth sits at a radiation balance between the incoming solar radiation. And if you remember in the last chapter, we looked at that 1,000 watts per meter, and we showed the different global warming effects, plus or minus just a percentage or two. An increase in global temperature could, in theory, be reduced by reflecting more radiation back into space. Reflecting just 2%, not very much, just 2% would be sufficient to offset the warming that may happen as a result of doubling atmospheric CO2 levels from their pre-industrial levels, which, we're just below 300, and the idea is, well, gosh, if you get above 600, you're really messing with the chemistry.
That's where the practice of cloud seeding comes from.
Right. So, as we did see in the last chapter, some human activities do give rise to cooling. As shown in figure 1311, the most significant is due to sulfate aerosols resulting from sulfur dioxide emissions. So that's one possible way, and there's even cloud ships is another one. How do you go up and just cool the air by putting little reflective particles way? Yeah. Well, we make snow to go skiing on our mountains. So.
Crappy show.
Yeah, well, yeah.
Well,
Crappy
that's
snow.
no.
Okay, so we spent a lot of time talking about carbon emissions. Now, what if we played around with electricity that didn't rely on CO2 at all? So here's a electrolyzer. So just very, very simply, you've got water sitting down here, in a tank, you send electricity through it, there's an anode and a cathode. Oxygen bubbles off on one, hydrogen bubbles off on the other, and away you go. So, and as that happens, let me just show you, there's kind of a cool, again, we're just going to touch on it, but I'm going to try to see if I can find a fuel cell animation. There's a few kind of cool ones out there. Yeah, let's just take this one little. Actually, I think I like this guy. Sorry about the cheesy music. So it sort of goes from chemistry to electrochemistry. So once you've separated the hydrogen, the electrons themselves flow through a circuit. The hydrogen comes through and sort of recombines. And so you've got chemical oxygen coming in, chemical hydrogen coming in over here. As the hydrogen, pause that. So again, chemical hydrogen coming in. Remember, hydrogen is just a proton and an electron. And remember, the only thing flowing through copper wires, light bulbs, etc., are just pure electrons. So it's kind of wild, but right here and it takes electricity to split this. So you kind of, in some ways, you're like, gosh, is this a perpetual motion machine? But anyway, as it comes in, the protons themselves migrate. Recombine with the proton. The oxygen is coming in, combines with the hydrogen, and then just off comes the water. So it's electrolysis in reverse. So this process is completely reversible. If you send electricity in, you split the water. When you allow the hydrogen and the oxygen to come back together, you make electricity. Yeah. So similar to what we were looking at before with the LED being sort of just the opposite of the photocell. That's how the electrolyzer and the fuel cell work in tandem. And he just called it a gas battery because as we know, hydrogen and oxygen are both gases at atmospheric temperature. Okay, so here's just another shot of that little video that we showed. There's a lot going on here, just showing just a lot of different chemistries for getting this thing to work. Just as you can go out and buy a lead acid battery or a nickel hydride battery or a lithium ion battery, a lot of different chemistries in this electrolyte where the hydrogen ions actually flow. So there again, that's that hydrogen proton that we saw a second ago. In the opposite direction, you've got some other kind of flow of a negative ion. So they both have to so it's a battery. It's a battery, but a chemical battery. Okay, so this is one vision of what a hydrogen economy might look like. Just a couple days ago, I was talking with one of my grad students, and he was sort of scratching his head over why our hydrogen truck is not driving around town. Well, it had problems with its various systems, as trucks do, and I'm not an auto mechanic. We took it over to Carl Tyler, like, nope, not touching that. Don't know how to deal with a hydrogen vehicle. So it's a little bit of a chicken and an egg thing, right? Where you need the technology, you need the technologists to get the whole system up and running. And there is, let me just show you this other kind of cool deal. Hydrogen fueling station in California. So this is happening. We were just checking this out in 241. So there's on the order of 30 hydrogen fueling stations in California right now. I think there's one, just outside of Reno. And what we'd love to do is, put our own on the map. I mean, we have one. It's not functioning, but the idea would be to get our own up and running. So these things are happening. So there's a picture of one, and just showing the different flows. The former dean of the Missoula College actually put together a plan just like this for Missoula. He had hydrogen-powered monorails, just like Disney World, Orlando. He kind of got himself crosswise with the provost, and now he's doing something down in Colorado. But he just had a book come out. His name's Paul Williamson. Big proponent for this type of economy. And during the, late 90s, early 2000s, there was a big push for this from like Honda and Toyota. And if I understand correctly now, Mitsubishi's got a production hydrogen car. And you can run it in two different ways. I mean, you can either run hydrogen to make electricity, like we just showed with the fuel cell, or you can just burn it in a combustion engine. So the truck we have out back is a combustion vehicle. So there's a pair of 5,000 PSI tanks in the back that run it up. We were just testing it the other day, and I thought one still had about 2K in it, but it didn't. Like, no smoking. Yes, ma'am. The only emission is water. That's it. If you burn too hot, you can run into the NOx issue where nitrogen will combine with oxygen, but at proper temperature, the only emissions are just hot nitrogen and steam and water. Yeah. Okay, so in this scenario, you can see that we're still sort of pulling natural gas, so we're still sort of in the fracking industry that can still go in to make electricity. Here's your CO2 coming out. Remember that red line? And so what I don't see is any CO2 like flowing off to a neat little greenhouse somewhere. I mean, that's where I'd kind of like to see it go. But anyway, it's going back underground, either for geological storage or enhanced recovery. But somewhere, let's see. Where's the so the hydrogen itself can either go into direct combustion, or the CH4, remember, has 4 hydrogens on it. So there's your hydrogen production facility where you're making hydrogen from methane. And if I understand correctly, the majority of the hydrogen for those plants that I just showed you, or the fueling stations in California, is coming from methane. It's not coming from water. But in an ideal world, and what I'm now also not seeing on this figure, and this is what I proposed to NASA a couple of years ago, did not get funded, but here was my little proposal. So you've got electrolysis. You've got water coming from the sky in raindrops. Right, so there's nature. It's not, I mean, you can call water alive if you're a hydrotherapist or whatever, but there's just plain old water coming coming from the sky. Then you've got your solar PV, and you've got your wind. Right, so here's your wind turbine spinning. Here's your PV panel running. electrons flow from these two technologies to split the water, O2, back to the biosphere, and H2 off to the technosphere. I think I even have this figure in my, but that, in my mind, like, how could it get more simple? Like, there's no carbon in this at all. You know, you've got hydrogen for transportation, you have hydrogen for heat, whatever, and really all you're doing is just taking good old water from nature, splitting it with electricity. Where's the electricity coming from? Well, it's coming from the sun and the wind. Yes, ma'am.
My question is,
Yeah.
what about water shortages?
What about water
Like we use oil.
Yeah, okay, so the question is, are we gonna run out of water? Is that the,
Well, will we put our water in places basically where that it's not
Yeah.
more usable for
well,
drinking and-
that's a good question, so, very, very fair question. Well, if this H2 heads off to our, Chevy Silverado, is our H2 truck. So there it is. Goes into the truck, and you move on down the road. This oxygen molecule is also coming back in, and H2O comes out the tailpipe.
Or just ran through a truck system.
It ran through a truck
That's
system.
probably going down the drain.
Well,
Right.
no, it's
Well,
when
not
it,
in the atmosphere, but-
yeah,
Yeah.
yeah, round and round she goes. Yeah,
Still makes me nervous.
Yeah.
All that water.
yeah, yeah.
It's pretty dangerous.
It's
I
a,
just heard that they're already doing that in China,
what's that?
splitting water.
Oh, sure, yeah, yeah.
Makes me nervous.
Yeah.
Well, what
The
about
way
like,
they do
re-
things over there, they're like,
what about like reverse osmosis, though, cleaning the water?
Oh, from the desalination
Yeah.
plants?
yeah,
Yeah,
it would be great to do something
Sure.
like that.
Even
Yeah.
though like it's way more expensive and it doesn't make sense to do it because it costs effective.
well, depends where you are, but yeah,
California.
yeah, yeah,
I think it's
yeah.
important to take risks to change the standards that go with water.
But,
Yeah.
yeah, this was my little proposal
I
to
think it's great.
NASA.
Better than the alternative.
Yeah.
Or that is the
Current.
alternative.
All right, so I think, is this a Tesla?
No, that's the,
What?
yeah.
Oh, they're kind of copy. I was lucky enough when I was there in Yellowstone over Thanksgiving break. There was a Tesla pulling in, and my one regret is I didn't get a picture of, because it's the Roosevelt Arch, and it says Roosevelt on the arch, and I wanted to have the name Roosevelt and Tesla in the same picture. But anyway, I got a shot of the guy driving in. It's turned out he was from Sheridan, Wyoming, and he said he'd had the thing since 2013 and loving it. The car we're looking at here, though, is a fuel cell car. So again, we saw a little animation of a fuel cell. So, and that's hydrogen and oxygen go in, electricity comes out. Here's a shot of a hydrogen bus. In London, there's your tanks on top. High pressure, maybe 5,000, maybe even 10,000 PSI. There's the Hindenburg.
We just watched the actual video for that in my journalism class.
Yeah,
Because the journalist guy who was covering that, when
Yeah.
that happened, the sound of his voice, like when he
Oh.
sees it, it's so
Yeah,
crazy. He
yeah.
just loses it. Oh.
well, and so this is again one of those kind of pick your poison in terms of, people die as a result of technology. Okay,
That
so,
was helium, right?
no, it's hydrogen.
That's
Hel-
hydrogen?
Yeah, if it were helium, it could not combust, yeah.
Oh, I thought helium was. okay.
No, helium is one of those noble gases that, yeah. As it turns out, helium's a cryogas, and there's a finite amount of it in the atmosphere.
Yeah, in
And
one place.
Well, it's everywhere, but.
In the atmosphere.
Yeah, but Texas has been, in the same way we looked at that air separation unit, if you cool it cold enough, the helium starts coming out too. Like 4 Kelvin?
Oh, wow.
Yeah.
Pretty cool.
Yeah, helium liquefies at 4 Kelvin, I think, if I'm not mistaken. Yeah. But, and it's, so for that reason, it's just more expensive, there's just less of it, and it takes more energy to purify it. Okay, so here's a shot of, what we might do to reduce energy demand. And I sit on this climate smart panel, and everyone says, oh, like the electric car is so sexy, and the LEDs are so appealing, and all the new high-tech stuff, but what about just boring old insulation and saving energy? It's just not as appealing, but this section 4.5 says, let's reduce the demand. And so this is straight out of box 14.5. It's called the 3-liter house. So thermal performance of existing buildings can radically be improved if they're adequately insulated. In the late 1990s, in the States, we're just showing some apartments here, and they look normal. In southwest Germany, it was giving a thorough thermal modernization. So 200 millimeters. So, gosh, that's not quite a foot, but, good 8 inches thick of foam insulation. You can see in this picture a guy putting in a, big foam insulator on the roof. Triple glazed windows with argon filling. So you mentioned helium a second ago. Argon also is inert, relatively heavy, and pretty expensive, and low emissivity. So not a whole lot of heating is going to go on. So cut back on heat last. Mechanical ventilation with heat recovery. So one thing I'm wondering about is I do see a stack here, but what you don't see are like a bunch of little stacks. There aren't many holes in the envelopes of these buildings. So, the air is getting recirculated. One issue with this, and if you take John Freer's building energy efficiency course, he'll talk about, the dangers. You can actually have mold build up, and as long as if you don't have proper ventilation. But that's that guy.
German playground's kind of sad.
Yeah, that's a little sparse on the playground, I agree. Yeah, there's only one, just go and swing by yourself. That's no fun. Yeah.
They just retrofitted the Empire State Building a few years back.
Oh, yeah?
Yeah, it's the most expensive green building in the world now.
Okay.
Apparently, it's going to take 3 or 4 decades to pay for itself, but it will pay for
Huh.
itself.
Huh, yeah. That's cool.
It's neat. You should look into it.
Yeah, I will.
It's
I will.
an enormous $400 million project. They retrofitted the Empire State Building to be the greenest building in the world maybe 4 or 5 years ago.
Yeah.
Really?
Yeah.
Growing plants on it?
Well,
No, it should be
The roof doesn't
insulation.
really work
Yeah.
like that.
Zero emissions building.
I'm
Yeah.
not being a smart ass, but I was just really curious, actually.
no, there are. Yeah, I'm glad you mentioned there are a lot of examples of zero emissions buildings.
Well, if I'm not mistaken, that's where the majority of our energy loss is.
It is.
Nationwide, right?
Yeah.
Yeah.
I'm not gonna say the majority, but it's the biggest sector.
Yeah.
Yeah, the biggest sector. All right, so that's this guy. This is looking, and I did a study like this a few years ago. This will be the last slide we look at. But when I was on the faculty at Drexel, I had some engineering students look at building a bicycle interstate, I wanted to call it, because I was trying to see what all the barriers were to more people not riding their bicycle. And typically, I'm going to get hit by a car, I'm going to get wet in the rain, I can't pedal against the headwind. So let's just build this separate elevated bicycle network, and then more people. And what you see on this graph right here at the top, this is megajoules per kilometer. All right, so if you remember from day one, we talked about that 10 megajoules per day. So you could take a figure like this and say, well, if I triple the length of it, how many kilometers can I ride my bike in a day, right? Because you're gonna burn that 10 megajoules of energy, and if you can go, gosh, so looking at this thing, if you can go 1 kilometer, and you're only gonna burn, what is that, 0.2, I'll just do the math really quick, and I'll let you go. You might see a question like this or two on the exam, on the final exam. But the point is, the bicycle is the most efficient. So 0.2 megajoules per kilometer. So 0.2 megajoules per kilometer. You can turn that around and say 1 kilometer per 0.2 megajoules. And if we multiply that by, make sure I did that right, 0.2 megajoules per kilometer. Multiply that by 10 megajoules. 10, let's do that math. 10 divided by 0.2 equals 50 kilometers. That's a pretty good ride. It's not a Tour de France effort, but anyway, so that's how you can show going 50 kilometers, and then what's that by 5/8? So is it how do you get divided by 8 times 5 equals it's a 31-mile ride, which would be a pretty good ride for most people in one day. Okay, well that's it. Let's on Thursday, we can wrap up some of these other next generation technologies. A lot of them we're going to cover in 102, but just bring any other questions you have about summaries or the last problem set. I'm happy to go over those too.
Cool.
All right.
You get that test up? Opening?
6?
Yeah.
Yeah, sure.
Excellent, thank you.
Yeah, do it right now.